This is Chapter 7, Lecture 2, Sediments and Sedimentary Environments. We'll pick up with fine-grained clastic rocks. Siltstone consists of very small grains, not visible without magnification of a hand lens. Mudstone consists of fine-grained sediment. That's a mixture of clay and silt. It's like shale, but the pieces are a little more rounded than shale. And then shale consists of particles too fine to see, even with a hand lens, like 1/256th of a millimeter. That's very small. Mudstone, shale, and mudrock are sort of used interchangeably. They all have, similar composition. Land environments include wind-blown accumulations, floodplains of meandering rivers, and bottoms of lakes. This is actually from Republic, Michigan. You can also get these rocks from soils that chemically weathered over time. And then silt, clay, and mud can accumulate along shorelines and offshore. This is a shallow sea or coastal mud flat. We have sediment accumulation on continental shelves, slopes, and continental seas. Lagoons trap fine sediment carried by streams, rivers, and wind. Deeper seas have fine particles carried by wind and ocean currents. Now my favorite, carbonate rocks and their landscapes. So these are not clastic, okay? They're chemical sedimentary rocks. They exist in many varieties, but most consistently they are composed of the mineral calcite. They're typically gray, but they can be white to dark gray, yellow, tan, and brown, depending on trace minerals found within them. And carbonate rocks might look like this in a landscape. Soluble limestone like this can dissolve quite easily at the Earth's surface in the presence of lower pH and dissolve even further into caves. We call that karst. Now we'll think about seas moving in and out. So this is what happens when a sea moves further into shore. At time 1, we have a shoreline separating a marine environment from a land environment, and then sand is deposited along the beach. The land is being eroded, so there's no sedimentary record of deposits there, but there is a development of an erosion surface. At time 2, the sea level rises, and so the sea and the beach have moved in across the land. The beach sand is now deposited over the area that used to be land, and then the left edge now has a nice coral reef. It's showing up right here. There's a lagoon between the reef and the shore. That's located where the sandy bottom used to exist, and mud is now being deposited over the older layer of beach sand. So first sand, now mud. Right? This is what you'd see in the sequence. At time 3, the sea moves farther inland, so the coral reef moves to the right. It's nearly over where the original beach was. The beach sand is now overlain by lagoon mud, which is overlain by limestone from the coral reef. And this is called a transgression, when you have the advance of a sea across the land. And if we were to just cut a section of these rocks out, and this is the section that we would see. So these are older units. We might not know what they are. They could be anything really, but sandstone is deposited, over which is mudstone, and lastly limestone. During a transgression, we expect to see those things in that order. But when seas move out, it's going to be somewhat opposite. At time 1, the sea moves out, it recedes, so the shoreline retreats toward the sea, and the beach and the lagoon follow. The sand that was close to the beach is now being eroded. The beach sand is deposited over lagoon mud, and lagoon mud is deposited over the reef limestone. Okay. At time 2, the lagoon mud builds out over the limestone. The beach sand now becomes coastal dunes that follow the shoreline toward the sea, and the beach sand and dune sand cover the lagoon mud, which overlies the limestone. At time 3, the sea is retreating further. Deeper marine sediment is overlain by shallower marine sediment or by land deposits, and then some layers can be eroded and removed. The sea moving out is called a regression. If we were to cut a section out from this, we would first see limestone deposited, then mudstone, then sandstone on top. So it's opposite of a transgression that way. So why do sedimentary layers end? It seems like a strange question, but they end because the types of rocks end. We call those facies. They're indicative of a sedimentary environment. A layer can also end because it was deposited only within a limited area, such as a river channel, like here. So there's limits. We don't have one type of rock covering the entire earth, of course. We look at different features to indicate the type of environment that existed in the past. You can look at color. Red means that a rock formed on land in an oxidizing environment. And gray probably indicates it formed underwater in a lower oxygen condition. And we can look at the size, shape, and sorting of sediments. That reflects the strength of the current of transport or the amount of transport. We can look at the thickness of bedding. Thicker implies bigger events, faster rates, or longer times between environmental changes. You can look at the type of bedding as well, and that reflects specific conditions of formation. You can look at mud cracks. Those indicate an environment that was occasionally wet but was able to dry out completely. So it would be a land environment at that point when you see mud cracks. You can also look at fossils. The types of fossils, whether they're land, marine, etc., indicate an environment as well. It also indicates possible climatic conditions. We can look at crossbeds to indicate the direction of current. They're inclined toward the direction in which the current flowed, left in this example. So I'm just going to show you with my pointer the direction of the current, because sediment would have been preserved in this direction, constantly eroding and being deposited here. So that's how I know the direction of the current, based on those crossbeds. We have something called clast imbrication in a river. And the idea here is that clasts normally lean toward the direction and that the current flowed, left in this example as well. With ripple marks, the steeper side of ripple marks indicates the current direction. The wind blew toward the left in this example as well. So we use all those things to understand where the current was coming from originally. Now there are resources in sedimentary rocks. Groundwater is a big one because most groundwater resides in open spaces and fractures of sedimentary rocks. Additionally, oil and natural gas form in organic-rich sedimentary rocks. Coal forms from the accumulation of plant remains in sedimentary environments such as swamps and deltas. Cement is produced from limestone. You quarry the limestone, crush it up, maybe do other things to it, but it's originally sourced from limestone. Salt forms in areas where salty water evaporates, such as shallow seas or closed basins on land. And then uranium actually occurs in sandstone and other sedimentary rocks, as well as in non-sedimentary environments. We can study the history of sedimentary rocks, where the present, what we see right now, is our key to the past. We study modern environments to understand what processes are occurring. And this is a picture of kind of the aftermath of the Indonesian tsunami. Past environments, we can look at those and study these ancient sedimentary rocks to understand how environments change through time. This is the Grand Canyon. We can look at past climate. By understanding the severity and causes of past climate changes, we can better understand future climate change. This is Georgetown Lake, Montana. Past events, we'll look at those by studying ancient deposits of geologic events, such as landslides. We can infer the processes that occurred and how those events impacted the landscape. We can look at sequences of events. Successive sedimentary rock layers give us clues about how environments changed over time. This is the Green River in Utah. And then ancient life. By studying succession of fossils, we can infer how life on Earth evolved. Now these are the sedimentary units in a block diagram west of Denver, Colorado. This is the Front Range, and that's mostly Precambrian metamorphic and granitic rocks. You can see that in gray. The red sandstone and conglomerate in blue were deposited on top of those basement rocks, right next to them. And then marine shale, beach and delta sandstone, river deposits overlie the red rocks. We have Red Rocks Amphitheater here as a cool example. The layers were folded, faulted, tilted, and they now dip towards the east. So folded, faulted, tilted. Green Mountain up here contains the youngest sedimentary rocks in the map area. The rock sequence continues into the subsurface where it's folded and faulted. Oil was actually found in this area by studying the sedimentary layers. Show you this Dakota hogback here sticking out, what that looks like. And then the I-70 road cut in the north here. Pretty cool. And you can look at a strat column or stratigraphic column or section here of the area. On top would be the youngest rocks. Like from Green Mountain, you have a Cenozoic conglomerate and sandstone. And then sandstone, shale, coal with plant fossils. Gray shale with marine shells, shark teeth, and fish bones. That means we were definitely underwater there. The Dakota Formation pointed out here, it has plant fossils, dinosaur tracks, and sedimentary features such as ripple marks. Morrison Formation has dinosaur fossils and tracks, so we're back on land. But then it will include shale, sandstone, and freshwater limestone as well in wetlands, rivers, and lakes. And then below that, we have mostly red, late Paleozoic, and early Mesozoic rocks overlying a red conglomerate and breccia. The upper part contains mudstone and marine limestone from a coastal mudflat. In the lowest sedimentary unit, the oldest sedimentary unit is a sequence of sandstone and poorly sorted coarse conglomerate and breccia. It was deposited by rivers and debris flow drained from the ancient mountain range called the Ancestral Rockies. So that's resting on the oldest basement rocks that are granite metamorphosed rocks as well. You can read it from bottom to top or top to bottom. Doesn't really matter. You just have to understand that the youngest is on top and the oldest is at the base in this one. We can also look at this depiction of Colorado's geologic history. This is the late Paleozoic. So we have some areas underwater that resulted in evaporites, and then on the edge of that sand, lime, sand, mud, lime from this, and then sand and gravel here. The sandstone and conglomerate shed off of the ancestral Rockies. That was the source for it. Salt and other evaporites formed in the inlets. And then in the early to middle Mesozoic, we have a continental environment with mud flats, sand dunes, lakes, and a river system, which deposit mudstone, sandstone, and conglomerate. Dinosaurs roamed this area as well. They would have left bones and trackways, on land. In the late Mesozoic, a shallow sea forms from the Arctic to the Gulf of Mexico, and then the Dakota Formation accumulated during the transgressions. So these are really cool. So we have the sequence of events for central Colorado, and then the sequence of rocks that should have resulted. And we will stop there for today.